Hello. So this is my very first video, and I hope it goes smoothly, and I hope that I make very little mistake. If there's anything, please let me know. So this is a past paper question, and it's from May 2009. It's time zone 1 and paper 1 question for HL. Okay, so it's a question on the complex numbers. Let's take a look. It says, if z is a non-zero complex number, we define L of z by the equation L of z is equal to ln modulus z plus I argn z, where argn z is between 0 and 2 pi. The first question says, show that when z is a positive real number, L of z will be equal to ln of z. Okay? So it's a 2-mark question, so it shouldn't be too complicated. Not to mention that it's a show that question, so you should be able to reason this out pretty quickly. But before we do this, we need to take a look at the question. What is it trying to do? So allow me to take up some space here. Basically, it seems like L of z is a new way of writing our complex numbers, because we've learned 3 ways of representing our complex numbers. I feel like it's a great luxury, I guess, for the complex numbers. We already have 3 ways of writing them, right? We have 3 forms of complex numbers, right? So, what is this focus? Okay, right. I hope this focus is fine. Forms of complex number. The first one is our Cartesian. Cartesian form, remember what it is? It's, let's use another color maybe. Okay, Cartesian form, we write it as A plus I, B, where A is our real part and B is our imaginary part. Okay. The second form is called the polar form, or we also call it the modulus argument form. Alright, so how do we write it? We have R and then cosine theta plus I sine theta. We also have a very special notation for this, which is R times cis theta, which is to say, when you see cis theta, you gotta translate it back to cosine theta plus I sine theta. Okay? We'll go over these forms again, so don't worry. Finally, there's my favorite form because it's the easiest to manipulate. Let me move it up. It's the Euler's form. So don't forget the new color, R, E, I, theta. Okay, so these are our 3 forms of writing a complex number. But the question, it doesn't seem like we can immediately translate this into any of the forms, can we? Right? So we have to understand what these 3 forms are, and we see that really they're all the same thing. They're just different forms, obviously. And that once we understand how we typically represent a complex number, we can easily go back to the question and try to fathom what it's all about. So let me remind you what our question, the form in our question looks like, right? It's something like ln z plus I arg z. Okay, I'm not saying that this is exactly comparable to any of these, but you'll see how they relate to each other very quickly, right? So the Cartesian form, right? So we know that, let's say if we have a complex plane, allow me to not use a ruler because eventually I'm going to stop using a ruler anyway. So let's say we have this argand. We have this plane, right? And remember what what used to be the x and y axes become once they become argand plane. The x-axis will represent, let me complete this. X-axis will represent the real numbers. Okay, we use RE for real, and the y-axis is the imaginary part of the complex number. So let's say if we have something of a radius of 1, okay, we would say that, for example, this point would be 1, the real number 1. But if we want to label the coordinate of this point, you would just have 1 and then 0, for example, right? Just as you were doing a x and y axis, it would be 1 and 0. And whereas instead of x and y, you would have real and imaginary, which means the imaginary part here, real part is 1 and the imaginary part is 0, right? And so if it's distance 1, this point would be I, okay? And so the coordinates, which reasonably should be this, 0 and 1. Okay, so if you use Cartesian form, it would be 0a plus 1i, right? And that gives you I, right? So you can say 0 plus I, something like that. And here it will be 1 plus 0i, which is 1, right? And so the same thing over here, it will be negative I, and this will be negative 1, okay? So all these forms can then relate to each other. So what do we mean by the modulus argument form? The modulus argument form, remember, it looks like this. The cis notation is, I don't really like it. I like the cosine and sine part because it really shows the structure of a complex number. So if we take a look at this, what it really is doing is that it's trying to look at, so for every complex number, if you want to plot it on the plane, you could always find, you can represent it with two things: the distance, the radius between that point based on the origin, from the origin, and the angle between that point and the real axis, something like that. So let me show you what I mean by that, right? So for example, let's say we've got two, we can, instead of thinking of this as 1 and 0, right? Let me label this negative 1, 0. This is 0, negative 1, right? So one thing that all these four points have in common is that the distance between, the shortest distance between them and the origin 0, 0 is just 1, right? We can think of this as a, let me use this fancy color, right? Let's say we could actually draw a circle of radius 1 around these numbers, right? So let's say this distance would be here. Distance is obviously 1, and it's like the radius, we call this radius, it's also 1, right? So in general, the distance between all of these numbers and the origin here, it's all 1. So what distinguishes them from each other is not going to be the distance, it's going to be the angle. So we need two parts to distinguish rational number, to find a unique point on the complex plane. To identify a unique complex number, we need two things: the radius, right, where it is in relation to the origin, and the angle, right? Suppose we have another situation where, okay, in this situation we have different angle, right? If we look at this angle here, recall your trigonometry, this would be 0, 2 pi, 4 pi, etc., right? You rotate around and around. One time you get 2 pi, a second time you get 4 pi, right? Whereas here, this point would be what? Pi over 2, right? We would have pi over 2. And what is the next one? 2 pi plus pi over 2 is Oh damn, I cannot do this math in my head right now. Okay, 2 pi plus, let's come back to this. So we add 2 pi, so for 5 pi over 2, right? Things like that, okay? And here, this point would be pi. The next one would be what? You add 2 pi, you get 3 pi, 5 pi, etc. And then this point, we could say it's 3 pi over 2, and then 7 pi over 2, and then you add another 2 pi, which is 11 pi over 2, etc. Right? So you rotate around this circle, you will get different angles. So what distinguishes each of these points, from each other, is the angle that you rotate to get to that point, right? So that's the idea of your complex number. And so there's another situation. Obviously, let's say, let me do a little tiny one over here. Let's say we have distance, radius, let's say 2, okay, over here, and let's say we have the same angle, okay, I don't know what this is, maybe pi over 4, okay, we have the same angle, but you could have distance 2, radius from the point, or you can have radius maybe, 3 or something, right? So basically this will make points A and B two distinct numbers, okay? So that's the idea of your representation of a complex number. You would need 2 parts to identify it completely. You would need the modulus part and the argument part. So the modulus refers to the distance, the r, the radius from the origin, and the argument refers to the angle. Okay, so let me remind you, and that's completely natural language, because modulus, as we recall, is the absolute number, and it's defined as the square root of the number squared. So this will promise that you get a positive number out of this operation. So modulus is the absolute value, right? And in our case, we can, in terms of complex numbers, we can think of the modulus as the distance or the radius of that complex number from the origin, right? And then argument is the angle, right? Angle theta, right? So yeah, so let's recall how to define all of these. Let's say, for example, polar number. Let's say, for example, right? I hope that it's focused. All right. Let's not move the focus too much because it's moving a lot. Let's say the number I itself, right? We've identified that the distance between I and the origin is just 1, and the angle, if it's not defined, if the domain is not restricted, it's any multiples. Sorry, pi over 2 plus 2 pi, right? 2k pi, right? So we would say we can write it as 1 times cosine. Let's say it's pi over 2, and then plus I sine pi over 2, right? And then we can see that, remember what your pi over 2 is going to give you 0, which is to say it doesn't have a real part. It's completely imaginary. So it's just going to be I sine pi over 2, and pi over 2 naturally, sine of pi over 2 naturally is 1, right? So that it makes sense if we represent I this way. And then it's super easy to represent I, right, as in Euler form. In Euler form, it's gonna be 1. It's still, the distance is still 1, and then EI and whatever angle it is. In our case, we have EI pi over 2. Right? So our conclusion is we can rewrite I either as 1i, which is the Cartesian form, right? So we can say it's 1i, or it's I sine pi theta with pi over 2, which is just 1, or we can say it's 1 times ei pi over 2. That's the gist of the forms of complex numbers, right? That's cool. So let's come back to this lovely equation here. Okay, so argument. So what does this equation say? Basically, it is in fact trying to mimic one of the forms, right? It's saying that, let's say L of z, this is the equation, right? It says it's L of z. L of z is really rewriting the ln of the modulus of the complex number plus I is just a complex number, and then argument of the complex number. So it's trying to mimic your modulus argument form, right? But in essence, all these forms are convertible, interconvertible, so it doesn't really matter which one you're looking at. But the thing is, you have to understand that this is argument, right? So basically what this question is saying that, okay, let's go back to the question, okay? So let me turn this page a little bit. I hope it doesn't leak. It's not leaking, is it? Alright, so our fabulous equation looks like this: ln of z plus I argument of z, right? So this is our argument, okay? And this is our modulus, right? So basically, we're looking at the polar form, and it says what? Show that when z is a positive real number, L of z is just equal to ln of z. Now that looks very simple. Once we understand what the notation ARG is, I think this is really what they want you to know. Basically, when z is a positive real number, it just means that it only has the real part, okay? And it doesn't have any imaginary part. So if it doesn't have any imaginary part, it must mean that, okay, so z is real, okay, implies that I times argument of z must be 0, right? It doesn't have any imaginary part, okay? Which is to say the argument of z is 0. Agreed, right? And which is to say, therefore, that ln of z, sorry, not ln of z, L of z is equal to ln of the modulus of z, okay? But another situation which is indicated in another condition is that it's a positive real number, which is to say that we don't even need the modulus, okay? So with or without the modulus, they're the same thing because it's always a positive number, okay? And so we can say that ln L of z is equal to ln of z. Done, okay? So that's the idea. So really, once you understand what the argument of a complex number is, you understand the difference between, how can we identify this? This is completely imaginary, this is the real part, then you can quickly go to the question. And by the way, you could also think about the diagram we had over there, right? So this is the real and this is the imaginary, and this is okay. So everything that is only real must lie on the real axis. It's just like there's no imaginary part. But then we can say this is positive real, this is negative real. So if it's a positive real number, it means that it must be somewhere over here, really, right? If it's somewhere over there, then what can you say, right? You know that it lies on that part of the axis, and as we've identified here, really, no matter what the point over here is, it doesn't matter what the radius is, the angle here is always going to be 0 or 2 pi or 4 pi, etc., etc., right? So, and then if you go back to the question, it does say that 0, right? It's between argument 0 and 2 pi. So therefore it has to be 0, right? So argument of z has to be 0, so we eliminate the other conditions. So it has to be 0, right? So even if you just do a sketch, you could quickly identify what the question is about, okay? So I hope this has been helpful, okay? Interesting, all right? So I think this is a really interesting question because it tries to come up with a new form for complex numbers, try to find a real interesting representation of real number. Now, the second part of the question, let's take a look. Use the equation to calculate L of -1. Okay, so what? Oh my God, what is this? So we're trying to see what this is all about, aren't we? Okay, so let me just use the other side. Oh, it leaks a little bit. Let's use another piece of paper. All right. So questions like this, right? If you don't even want to think, the best thing you can do is just to plug in -1 and see what happens, right? So you have ln of -1 and plus I argument of the complex number -1, right? And what do we need to do? Looks like a huge conundrum, doesn't it? So what does it say? What does this equation tell us now? Okay, so -1 means that it's a number with really just real part and there's no imaginary part, right? So then what can we do? First of all, the first part is easy because ln of -1, right? It's just going to be ln of 1, right? Now the tricky part is to identify what do we mean by the argument of -1, the real number -1, right? So if we go back to this plane, polar, we see that -1 is over here, and this is our I. Okay, I always like to use this diagram because it really helps let us see the things very quickly, right? So we already identify the angle here has to be, right? It has to be all the way here. It has to be pi or 3 pi, etc., etc. But because we've restricted it to 0, between 0 and 2 pi, so the only choice we got is pi, right? So it means that the angle of this particular complex number, which is a real number in our case, of -1, it has got to be pi. So this has to be plus I of pi. All right. But you can be more technical, of course. Ln of 1 is, of course, just 0. It means e to the power of 0 gives you 1. As a reminder, right? Ln of 1 is 0 because e to the power of 0 is 1. Okay? And this is plus I pi, therefore this is just equal to I pi. Excellent. Okay, so ln, so it just means that if we represent, if we want to represent the real number -1, we can rewrite it as a number with just I pi, right? The distance is 1 and the angle is pi, right? Let's move this above a little bit. Now the second part, L of 1 -1. Okay, so the complex number in question here is, let me use another part. The complex number in question here is 1, okay, and minus I, right? So the real part, so we can identify this on our plane, okay? 1 and -1. 1 is here, right? And negative, you remember, this is 1, this is negative I. So it's in fact the complex number that is here, right? It's gonna have real part 1 and our complex number -1, right? Because it means that it's 1 plus I -1, right? In terms of our Cartesian form, sorry. In terms of our Cartesian form, it looks like this. So we can identify that it's 1 and -1 over here. So now our job is to look at the argument and the radius, right? And the modulus, basically, right? So we are trying to look at, okay? Basically, again, complex numbers work a lot like vectors. It's like adding a +1, and then you go down a -1 over here. So we're looking at the angle over here, right? Because the angle restriction is from 0 to 2 pi, right? So here, let me see, okay? So this part, it's going to be 1, and this part is going to be 1, right? 1 and 1. So in effect, we're looking at a triangle with 1 and 1, and here's 90 degrees. So what can we do? First of all, this part, the radius, modulus, sorry, let me cross this out. Modulus is gonna be square root of 1 plus 1. Of course, that's just square root of 2. And then the angle here, right, it's going to be 45, 45, which is pi over 4. But we don't want a negative angle, so we got to do, how do we do it? 2 pi minus pi over 4, right? That's going to be 7 pi over 4. This is our argument. Okay, my argument, and this is our modulus of z. Right? So we've identified the key features of this complex numbers, and now we go back to the equation. It says that ln of the modulus of this thing, right, plus I argument of this thing, right? So the modulus of this complex number is just gonna be ln of square root of 2, right? And the argument of this complex number is gonna be 7 pi over 4. Okay. So that is that. Alright, so that's our answer to this part. Okay, so in effect, again, if we know what a complex number looks like, we know how to represent it in this function. This function says divide it into the real part, the argument part, sorry, the modulus part and the argument part. Okay. Finally, we have -1 plus I, right? So -1 plus I. Let me put it on the same sheet. Where is it? -1 is over here, and plus I is over here. So again, it's here, it's 1, and here is 1, right? It's this one. This angle here has to be what? Pi over 2 plus pi over 4, which gives you 3 pi. Sorry, is it 3 pi over 2? I'm terrible at this. So you could do pi minus pi over 4, which is gonna give you what? Okay, pi minus, so the modulus of this one is gonna be square root of 2, and the argument of this one is this angle, which is pi over 2 plus pi over 4, which is 2 pi over 4 plus, yeah, it's gonna be 3 pi over 4. Yeah, I hope that's okay. Alright, so then we have therefore L of -1 plus I is equal to ln, again, square root of 2. This time it's I 3 pi over 4. Okay? Excellent. And so now that we've done, okay, let's circle this, and this is our final solution. Here we say this is equal to L of 1 negative I, right? Okay, so now let's keep this notes here, and let's take a look at the final question. Show that L of Z1 times Z2 is equal to L of Z1 plus L of Z2. It doesn't hold for all values of Z1 and Z2. Now, a keyword in this question, of course, is hence, which is to say, to use our information from what we got previously, right? So what can we get? What have we got previously? We've got this one, and this one. So what does it mean? If you're sharp enough, I mean, you gotta take a look at the relationship between all three complex numbers identified here, right? We want to use L of Z1, Z2. So you can see that the negative, right? If we have 1 minus I times negative 1, we get negative 1 plus I, right? So which is to say, if our Z1, right, if our Z1 is this, and if our Z2 is this, then this one would be Z1, Z2, okay? Excellent. So we want to show that L of Z1, Z2, okay, we want to show L of negative 1 plus I is not equal to, okay, it's not equal to L of negative 1 plus L of Z2. Sorry, Z2 is our 1 minus I. Right, we want to show that this equation doesn't hold. So we already identify L of Z negative 1 plus I here, right? So this part is ln of square root of 2. So we say left hand side ln of square root of 2 plus 3 pi over 4. Okay. How about right hand side? What have we got? So what is our L of negative 1? L of negative 1 is just I pi and then plus ln, here we have the other one, ln of 2 plus I 7 pi over 4. Okay. So right hand side, we simplify this a little bit, which is equal to ln of square root of 2 plus I of 7 pi over 4 plus 1, which is gonna be 4 plus 4. I suppose it's 11 pi over 4, right? Oh, and what a pity. These two are not equal, which is not equal to left hand side, okay? That's it. So we've shown a counterexample of that statement, right? And therefore, not the case that L of Z1, Z2 equals to L of Z1 plus L of Z2. Okay. I hope this is clear enough. So I can't believe I spent 30 minutes on this question. But basically, what I like about this question is that it tries to really ask you about knowledge of this thing, right? It tries to, first you have to recognize this is really the modulus of a complex number, which is gonna be the modulus in the polar form, and this is evidently the argument of the complex number, which is gonna be the angle from which the angle between the complex number and the real number axis, right? And so you always remember, you can always convert complex numbers in between three forms, right? And so it's kind of a very interesting case. All right. So I hope this has been clear, and I do wanna, if we have enough time, I do want to talk a little bit about the Euler form. Anyway, I think that could be for another video because this one is too long. So let's do another video instead. See you later. So let me cut this off.